In this lesson, we're going to cover limits at infinity and horizontal asymptotes. So this example says, consider the function f of x equals the square root of 2x squared plus 1 all over 3x minus 5. Part A says, find the horizontal asymptotes of the graph of the function. So I flipped back to the front side of the notes, and I wanted to look one more time at the definition for horizontal asymptote. So your horizontal asymptote is going to be any line y equals L, where either the limit as x goes to infinity of f equals that value L, or the limit as x goes to negative infinity of f equals that value L. So we're taking it back to these two limit definitions for a horizontal asymptote. So what we're going to do is we're going to take the limit as x goes to positive infinity of this function. Then we're going to do the same thing, but it's going to be the limit as x goes to negative infinity of this function. Just like the previous problems, in order to evaluate this limit at infinity, we're going to divide the numerator and denominator by the highest power that's in the denominator. So we're going to divide the numerator and denominator both by x. So I set it up where we're dividing the numerator and the denominator both by x, which is the highest power in the denominator. You can see that in the denominator, this is no problem. But the numerator is kind of funky. In order to divide the numerator by x, because there's specifically a square root, I'm going to put a little definition right here. The square root of x squared is equal to the absolute value of x. So back in your Math 3 class, we kind of sheltered you guys. I feel like most teachers, when they do the square root of x squared, you just write x as your answer. But algebraically speaking, you're technically supposed to use absolute value to indicate that there's no negative underneath the square root at any point. And if you rewrite this using absolute value of x, then from earlier in our chapter, that requires you to use the definition of absolute value. The absolute value of x is equal to a positive x when you're going to the right, but the absolute value of x is equal to negative x when you're going to the left. And again, that was because this graph is a V, and to the right, the slope was positive, and the left side of the graph has a negative slope. So it's written as a piecewise. When we do this part of the problem, it's not going to make much of a difference. But when we go x goes to negative infinity, it's going to generate a negative in the problem, but we'll deal with that in the next part of the problem. So for now, I just want to point out that x is equal to the square root of x squared. So when we divide by x, to bring this x under the square root, we're actually going to divide both of these terms by x squared, because the square root of x squared gives you this x. So again, in the denominator, you're dividing both of these terms by x. So you get this, and that's pretty straightforward. In the numerator, because you have the square root, when you divide by x, you have to think about first bringing the x underneath the square root, and bringing an x into a square root makes it an x squared instead of just x. And that's why we're taking both of these terms and dividing them both by x squared. Okay, now we're going to simplify each term. Okay, so at this point, to evaluate this limit, we're going to take the limit of the numerator and the limit of the denominator. When we take the limit of the numerator, we're going to bring the square root to the outside and then take the limit of each individual term. Okay, so you can see I pulled the square root to the outside. I took the limit of 2 and then the limit of 1 over x squared. In the denominator, we have the limit of 3. And then for this fraction, I pulled the 5 to the front of the limit and then just took the limit of 1 over x. So now as x gets larger and larger, this goes to 0. This whole thing goes to 0 as well. And now all we have left is the limit of 2 is just 2, but it's underneath the square root. And then here the limit of 3 is just 3. So our final answer is the square root of 2 over 3. All right, so similarly, we're going to do the same thing, but this time the limit as x goes to negative infinity of the same function. So we start by dividing the top and the bottom by the highest power in the denominator. So when we distribute 1 over x to both of these terms, you get 3 minus 5 over x. When we divide the numerator by 1 over x, we bring in x squared because it's underneath the square root. And because of this definition up here, because x is going in the negative direction, it generates a negative in this problem. So you just stick a negative in front of the expression. So I simplified this fraction to just get 2. In order to evaluate this limit, we're going to do the limit of the top and the limit of the bottom. When we take the limit of the top, we're going to pull this negative to the front of the limit, and we're also going to pull the square root to the outside of the limit. Then we're going to take the limit of these individual terms. Okay, at this point, we have the limit of the constant is just equal to that constant, so both of these are just going to become 2 and 3. Right here we have the limit as x goes to negative infinity of 1 over x squared. So if you remember the graph for 1 over x squared, we go 1 over x squared, memorize that. You're going to the negative infinity, that means the graph is approaching a height of 0. So that means this just goes to 0. Down here we have the graph of 1 over x. Again, you want to memorize this. X goes to negative infinity, so this graph approaches a height of 0 as well. So this term will also go to 0, and then we end up just getting negative the square root of 2 over 3. So we end up getting that our horizontal asymptotes are y equals plus or minus root 2 over 3. Finally, part B says identify the vertical asymptotes of the graph of the function. So let's go back to our original function. We have f of x equals, and we have this expression. So our vertical asymptotes, recall, are going to be what makes the denominator equal to 0. So we end up getting x equals 5/3. This problem says find the limit as x goes to positive infinity of f of x. Also, we're going to find the limit as x goes to negative infinity of f of x. We're also going to find the x and y intercepts for the function, and then we're going to use all of that information to sketch this curve. So I wrote it out. We have the limit as x goes to infinity, and then I wrote out the function. Because we're taking the limit and we have a product of functions, we're going to rewrite this as a product of their individual limits. To evaluate these limits, I drew graphs for each of these. We have 1 minus x, and it's going to be a straight line, hits the y-axis at 1, and has a negative slope. Here we have x minus 3 quantity squared has been shifted to the right 3, and it's a parabola. And then x minus 5 quantity squared is shifted right 5, also a parabola opening up. So as x goes to infinity of 1 minus x, you can see that this graph, as you go to the right, is going to approach a height of negative infinity. Next, the parabola x minus 3 quantity squared, to the right, this graph is going to go up to infinity. And the same thing for this last one. And just a reminder, infinity is not a number, so technically we can't multiply infinity and get infinity cubed. It's just a concept. But regardless, we have a negative value that's growing without bound times another value that's growing without bound in a positive direction times one more is going to give us ultimately negative infinity. What this means, as x gets larger and larger in the positive direction, the height of the graph is going to go to negative infinity or go down. So we're going to do the same thing, but in the negative direction. We're going to look at each of these in the negative direction, but first let's rewrite it using a product of their individual limits. So as x goes to left, this graph is going to go up. As x goes to the left, this graph is also going to go up to positive infinity, and similarly for the last function. So our final answer is positive infinity. So that means as x goes to negative infinity, the height of the graph is going to go to positive infinity or up. Next, we want to find the x-intercepts. And to find the x-intercepts, we're going to plug in 0 for y. So first we have 1 minus x equals 0. When you add x over, you get x equals 1. Next, when we set this equal to 0, we're going to get x equals 3. And last, we're going to get x equals 5. And I made a note, the graph will bump at x equals 3 and 5 because these factors have even multiplicity. And that's because their powers are even. If the powers were odd, the graph would cross through at those corresponding x values. But because the powers are even, the graph will bump there. So anytime you have a power that's even, 2, 4, 6, and so on, the graph will have a bump. Anytime your powers, like this one is technically a 1, anytime your powers are odd, like 1, 3, 5, and so on, your graph will cross through at that corresponding x value. Okay, next we're going to find the y-intercept. To find the y-intercept, we're going to plug in 0 for x. Let's go ahead and simplify this. So we end up getting a y-intercept of 225. Okay, to recap, as x goes to the right, the graph is going to go down. As x goes to the left, the graph will go up. Your x-intercepts are 1, 3, and 5 with a bump at 3 and 5. Your y-intercept is a height of positive 225. And now let's go ahead and draw a rough sketch of this curve. So our intercepts are at 1, 3, and 5. To the right, the graph is going down. We have bumps at 3 and 5. So the graph is going to bump here, turn, bump again, turn, and then the graph is going to cross through and then keep going, and it hits the y-axis at a height of 225. Here's a really basic sketch, not drawn to scale, of our curve. And thanks for watching, guys.